This presentation is intended to remind you of some of the major themes we have talked about thus far in the class. We will start by recapping the fields of descriptive and inferential statistics. Descriptive statistics focus on the tabulation, presentation, and summarization of measurements. Simply put, this focuses on describing a sample. We have talked about the real-world limitations that make conducting a census unfeasible, leading us to collect a sample and use inference to make a conclusion about the entire population. The field inferential statistics utilizes techniques to make generalizations about a population from a sample by estimating population parameters and testing hypotheses. We use inferential statistics to account for the differences that are known to occur because we are sampling a population instead of taking a census. Because we are sampling, our sample will not perfectly represent the population, and that is why we use inferential statistics to characterize this uncertainty. The thing to remember is that we start by trying to generate a representative sample of the population. We must then meet the assumptions of sampling that our sample is unbiased and representative. If we meet these assumptions, we can use the inference they afford us to draw conclusions about the population from our sample. Now we will review what a normal distribution is and the probability theory that allows us to utilize its concept in sampling. A normal distribution, or the normal frequency curve, is generated by the displayed equation. Although this equation is important and generates the shown distribution, I will never expect you to memorize such things. I do, however, expect you to remember that the math of a normal distribution results in a symmetrical, bell-shaped curve around the mean. For each population mean and standard deviation, there is a normal distribution curve generated. This means that the mean controls the middle location of the distribution, and the standard deviation controls the width of the distribution, with a larger standard deviation resulting in a more spread out distribution. All normal distributions will demonstrate the following properties. The curve is symmetrical about the mean is at the middle and divides the area into halves, the total area under the curve is equal to 1, and it is completely determined by its mean and standard deviation. If we look at a cumulative distribution function, we see that 50% of the values are less than the mean, and 50% of the values are greater than the mean. Additionally, when looking at a normal distribution, we can count on the fact that 66% of the possible outcomes will fall within plus and minus 1 standard deviation of the mean, 95% within 2 standard deviations, and 99.7% of the possible outcomes within 3 standard deviations of the mean. If we roll a pair of dice 10 times as a sample, we get the following set of values: 10, 4, 12, 10, 11, 4, 12, 4, 7, 9. From these, we can calculate the sample mean as 8.54, which differs from our expected population mean of 7. But if we roll that pair of dice, say 200 times, probability tells us our sample mean should approach the population mean, and we can see that eventually it does. This foundational assumption of all probability-based sampling is called the law of large numbers, which states that as the sample size increases, the sample statistic will approach the population parameter regardless of the population distribution. Now let's look at the set of 10 dice samples in a slightly different way and take 10 independent sets of 10 dice rolls. We should think of the average of each sample set corresponding to a possible value as belonging to a distribution we call the sampling distribution of the mean. If we look at how the mean of the means from the sets of samples changes, it approaches the population mean fairly quickly. Once we take a sample that is large enough to average out outlier values, the sample distribution of our statistic will be normally distributed, where the sample estimate of the population mean will be approximately the population mean, and the standard deviation of the statistic will be represented by the standard deviation divided by the square root of n, which we more commonly refer to as the standard error. If we think about the pair of dice experiment, we get these curves for the variable distribution, which represents the possible outcomes of a single sample, and sample distribution, which represents the possible sample means if little n equals 10. This narrowing of the sample distribution from the variable distribution is referred to as the central limit theorem, which states that if a sample with a sufficiently large sample size, the sampling distribution will approximate a normal distribution. Let us take a moment to refresh how these theories control our sampling distributions. First, the law of large numbers allows us to assume that by collecting enough samples, our sample mean will provide a good estimate of the population mean. And second, the central limit theorem allows us to assume that a large enough sample provides us a sampling distribution that will be approximately normal no matter what the population distribution looks like. Together, these theorems mean that even if we do not know the shape of our population distribution we are sampling from, we can draw inference about a population if we take enough samples to assume we are approximating the population mean and that the sampling distribution is normal in its shape. However, as with most things in sampling, we have a couple caveats to consider. The first to keep in mind is that if the population is normally distributed, then the sampling distribution will be normal at any sample size. And secondly, what is a large sample? Most statistics books will say when little n is greater than or equal to 30, we can invoke these ideas. However, things are not that simple in practice. The thing to remember is that as a variable's population distribution becomes less normally distributed, more samples are required to invoke these theories. This means we need to use our judgment and knowledge as managers to determine how variable we think a population is to determine how many samples are needed to invoke these ideas. Now we will refresh the ideas underlying the Z and T distributions. Since each combination of population means and standard deviations results in a uniquely located and shaped normal distribution, where the shape is controlled by the standard deviation, we need to take advantage of this symmetrical shape to the distributions to determine the percentage of values that lies between 2 points in the distribution. However, to do this, we have to find a way to standardize the distribution. This standardization is called the standard normal distribution, which is a normal distribution where the mean equals 0 and the standard deviation equals 1. You might be more familiar with this being called the Z distribution. The key to finding the probability of a certain range of values with the standard normal distribution is passing our mean and standard deviation to the standardized variable equation, where Z equals the number of standard deviations that the X value is away from the mean. Once you calculate a Z value, the percentage it represents can be found in a Z table, but be careful as these tables can vary in their interpretation. However, in order to use the Z distribution to determine these probabilities, we have to know the population mean and standard deviation. Generally, we do not know the population standard deviation and mean. Without these, our confidence level comes from the T distribution, which is derived from the T statistic. The distribution produced by the formula is a symmetrical curve with a mean of 0 that has its width controlled by our degrees of freedom, which equals little n minus 1. The differences we see in this set of curves results in the tails of the distribution having higher probabilities. If we compare the statistics from the z and t distributions at a 95% probability, the z statistic is plus and minus 2 standard deviations of the mean, while the t statistic requires us to define our sample size, and if we set it at little n equals 10, we get plus and minus 2.26 standard deviations of the mean. This means unless we have a significantly large sample size, that our t distribution will produce a larger confidence interval than the z distribution because of the added probability in the tails. Let us recap how all of this impacts our ability to sample. What if I had to tell you to shoot at a bullseye without knowing where the bullseye was? This is the case in sampling since the bullseye is unknown, meaning assessing the accuracy and precision of a statistical estimate is not very simple. The spread reflects the precision of the process, but the holes from the arrows only provide an estimate of the bullseye's accuracy. A confidence interval allows us to estimate the true value, or the bullseye, without knowing anything about the population distribution. This estimation process belongs to the techniques of inferential statistics, which help us determine how well our sample approximates the population. More simply, it allows us to describe the range of possible values an unknown population parameter could have. Beyond estimating the parameters we are interested in, we want to be able to assess how effective and efficient a sampling procedure is at estimating this parameter. Essentially, we want to know which procedure will get us the best answer for the least work. When we look at how efficiently a statistic provides an estimate of a population parameter, two things interact to control this process: the population variability and the sample size. A general rule of sampling is that as a population's variability, or the range of possible values an observation can have, increases, the number of samples necessary to achieve a desired precision also increases. Meaning, the larger our population standard deviation is, the more samples we need to be precise. In a connected way, we can also say that as a sample size increases, the precision of our estimated population parameter will increase, meaning that at some sample size there will be a decline in benefit to sampling anymore. The difference in thinking about this between stats theory and the real world is the recognition of constraints on our sampling process. Stats theory would have us sample until we hit diminishing returns in our accuracy. The real world would have us stop sampling when we hit a constraint to our sampling process.